We are doing thermistors today, so we had a look at the potential dividing circuit last lesson. So have a look at the graph here on the left. It shows that the resistance of the thermistor is dependent on the temperature. You can see that as the temperature is increasing, the resistance of the thermistor is going down sharply. So, and that's why we use it in a circuit. So we can actually control, let's say we have an air conditioner. We want to set the air conditioner to a particular temperature, and we want the air conditioner to shut off or stop blowing out cold air if that temperature has been reached. But if it gets warmer, if the temperature increases, it'll get into action again. If the temperature falls down or to that level, we need to stop the voltage supply. So that's exactly what this thermistor does. So let's have a look at this circuit. So we put the thermistor in series with another resistor where we've actually taken the output. So we'll have the air conditioner here somewhere. So what will happen is, we know that in a series circuit, voltage is shared, and the higher resistance gets higher share of the input supply. So in this circuit, if the temperature is high, so if it's getting really warm, don't you want your air conditioner to work? So you want the V output to be enough for the air conditioner to work. So at a higher temperature, we can see that the resistance of the thermistor goes down from the graph. So if the resistance of thermistor is less at high temperature, the air conditioner, where we're getting the output, will actually get the highest share of the input supply, and hence the air conditioner will work. Now, what happens when an optimum temperature is reached, or there's low temperature in the room now? So if the temperature is low, the resistance has a high, thermistor has a high resistance. So now thermistor starts getting more share of the input supply, and the air conditioner, where we're getting the output from, gets less share, so it'll shut down. So it won't actually continue to blow. So this is how we use a thermistor in a potential dividing circuit to manage what temperatures we want the device to work and when we want it to shut down. So let's have a look at an example. So we have a potential dividing circuit here, and we've been given the graph for the thermistor's resistance as well. So a potential divider circuit includes a thermistor as shown. Find the resistance of the thermistor at 30 degrees Celsius. So you'll actually find from the graph, at 30 degrees Celsius, the resistance of the thermistor is, we can see it is 15 kilo ohms. See, the units here are kilo ohms, so be mindful of that. Find the current in the circuit at 30 degrees Celsius. So we know, using Ohm law, it's 10 here. So I equals V over R. So we're finding the total. Total input voltage is 10, and the total resistance will be the resistance of R1 plus R2. Now this is 10 kilo ohm. Sorry, what am I doing? This is not 10 kilo ohms. So at 30 degrees Celsius, what's the resistance of the thermistor at 30 degrees Celsius? So the total resistance will be 5 kilo ohms, so that's 5,000, plus the resistance of the thermistor. So at 30 degrees Celsius, resistance of the thermistor is 15 kilo ohms, so 15,000. So that is the current in the circuit. So we find that. So that is 0.0005 amps, or which is also 0.5 milliamps. Now we need to find the V output. Now remember that short formula for V output that we calculated. So V output is, which resistance are we finding the V output across? 5. So 5 kilo ohms over the total. So at 30 degrees, what's the total? 5 for the resistance, and thermistor is 15 times the V input. Now you must have noticed that I did not convert the kilo ohms into ohms in this case, because both the top and bottom of the fraction, so this the R1 over the the 5 kilo ohms and 5 plus 15 kilo ohms, they're both in kilo ohms and they're being divided, so that's fine. You don't really need, as long as they're both in the same units. So it'll be 50 over 20, so that is 2.5 volts. So you can see that at 30 degrees Celsius, the output across the 5 kilo ohm resistor is 2.5. Now let's see what happens at 20 degrees Celsius. Let's first predict what will happen. As temperature is going down from 30 to 20, what is happening to the resistance of the thermistor? Isn't it increasing? So as temperature is going down, resistance of the thermistor is increasing, so the thermistor will get a higher share. So we should get a lower value of V output than 2.5. But let's have a look. Let's see if it actually is true. So V output at 20, so resistance is 5. Total is 5 plus. Now what's the value of the thermistor's resistance at 20 degrees Celsius? It's 20 times V input. So it's 50 over 25 and V output is now only 2 volts. So we can see as the temperature is decreasing, the V output is getting a lesser share of the input supply. Out of the 10 volts, it was getting 2.5 at 30 degrees Celsius, but at 20 degrees Celsius, it's only getting 2 volts. Because that's the temperature, as the temperature is decreasing, thermistor is increasing its resistance. So it gets a higher share of the input supply.